Hello, I'm Irvin. I'm here to turn mathematics upside down. So bear with me for the next 5 or 10 minutes. In my opinion, math education in the United States may be of little match against that of other major countries. This observation is drawn from analyzing YouTube presentations of solutions to numerous math problems. The foundations of our math are based upon interpretations that can be easily refuted. I question my own presentation because it is based upon my interpretation. However, I give refutations of the existing approaches and back up my own proofs and alternate ways of looking at a concept. While the teaching of today's math is based upon memorization of manipulatives, some students still grasp a deep understanding based from what they were taught. My approach presents a different way of teaching and thinking about math that allowed me to get far beyond what I was taught. Because I have read this presentation dozens of times, it is so easy for me to understand. If you would like to benefit from viewing this presentation as I did, you will have to view it many times and duplicate my work. Beware though, it could dramatically change your thinking processes. Let's question some math interpretations. Zero is nothing, signless, and a special placeholder. The proofs that are given is 0 plus 5 is 5. I haven't found a proof that shows it's signless. And as a placeholder, 105, if we leave the 0 out, it becomes 15. I think this is all rubbish. Let's look at each of those three statements. If 0 plus 5 is 5, then 1 times 5 is 5. It would be absurd to say that 1 is nothing. 12 plus 5 modulo 12, or clock arithmetic, is equal to 5. Maybe 12 is like nothing. Is it like 0? Yes, it's the integer before 1. The sign proof. 0 plus 2 is equal to 2. Then by subtraction, 0 is equal to 2 minus 2. Minus 2 plus 2 equals 0. And by subtraction, minus 2 is equal to 0 minus 2. That's the definition of a negative number. If now instead of using, we replace that by 0, we get 0 minus 0 equals 0, as we would expect. But 0 minus 0 would also be minus 0. The algebra and the picture validate the interpretation that 0 has a sign. We look at the function 1 over x in the picture. As we approach 0, we see their 0 approaches a positive value and a negative value. We could interpret 0 as the beginning of the positive numbers and minus 0 as the beginning of the negative numbers. Now let's look at 0 as a placeholder. The number 125, if we drop the 2, we also get 15. Now, as a placeholder, I'd like to look at another proof. This is a bit more complicated. If we take the number 121 in the base 9, that's 1 times 9 to the second plus 2 times 9 to the first plus 1 times 9 to the 0th power, which is 81 plus 18 plus 1, which is 100 in the base 10 power. Definitely much more complicated than base 9. If we take 11 in base 9, we find that's 1 times 9 to the first plus 1 times 9 to the 0, which is 9 plus 1, which is 10 in the base 10 system. We take a look at 10 in the base 9 system using the same number structure. We come out that that's 9 plus 0 is also equal to 9. Now let's take a look at 10 times 10. That would give us 100, which would be 1 times 9 to the second power plus 0 times 9 to the first power and 0 times 9 to the 0 power, which gives us 100 in the base 9 system. 9 times 9 is 81. So they're both equal to the same value. Now let's multiply 10 times 10 to the base 9. It is 11. So 1 times 11 is 11. Times 11 is 11. We have to move it over one space because we're not using 0 to make our numbers. We add that up, we get 121. Now let's do this arithmetic in base 10. A bit messier, but we get 100 as we expected we would. In the base 9, 0 is the integer before 1, but it's not used to create numbers. If it is, then it creates an ambiguity. 9 in the base 9 system is 9, and 10 in the base 9 system is also 9. Since the 0 is not needed to create numbers, it should not be considered a placeholder, though it could be if you so choose to believe that. And we give 2 multiplications showing where we're using 0 as a placeholder and where we're not using it as a placeholder, how much easier the arithmetic is to do. Now, let's look at multiplication, see what the impact of 0 is on that. For multiplication, we count the number of operands. So 3 times 2 is 3 2s is 6. 2 3s is also 6. The computing property is satisfied. It looks like a good definition to define multiplication. However, if we define it as the counting of the operators, then we have 3 pluses, and that gives us 8 as the answer. And 2 times 3, 2 pluses, that gives us 9 as the answer. It's not commutative. That's why we don't choose this as a definition of multiplication. If we redefine multiplication, it's 3 times 2 as 0 plus the 3 2s, we get 6, and 2 times 3 is also 6. So just a slight change in multiplication keeps us mentally consistent. And we use pattern recognition. In pattern recognition, 3 times 2 is 2 plus 2 plus 2. Work our way, 1 times 2 is 2. But to get to the next step, we have to drop 2, where we've been dropping plus 2 all along. If we have the new definition of multiplication, we get down to 1 times 2, all we have to do is drop a plus 2 and we get 0. We get the same answer both ways, except with a little bit of extra interpretation. Let's look how this works with exponentiation. 2 to the 3rd power is multiplication of 3 2s. An alternate definition would be 1 times those 3 2s. And as we drop the time 2s, we aren't consistent, we get 0 as the answer. In this case, we get 1 as the answer, and 2 to the 0th power is 1. The first 2 examples, if we break pattern, we get the correct answer. The last 2 examples, if we break out it, we get the wrong answer. In our current textbook, 0 is defined as the identity element for addition, and 1 is defined as the identity element for multiplication. To check my own consistency in math, you'll notice, again, starting with 0 plus 1 is equal to 1, 0 plus 0 is equal to 0. We would call that 2 times 0. But in my notion, it's really 1 times 0. But if we follow it through, we run into no problem. From this, we use the commutative property to prove that 0 times 2 is equal to 0. However, when we extend the definition of multiplication, we prove that 0 times 2 is equal to 0, as we've done in this case. With the right definition of multiplication, we do not need to use the commutative property. Let's look at this with another approach. There are conditions for multiplication in which we get a count of 5. You only really need 2 of them, because definition is key to understanding math. It has to be closely scrutinized. A plus 0 equal A, and A times 0 equals 0. The basic interpretation that is 0 is nothing. However, with the definition of multiplication we have, we don't need to base multiplication on that. So we've defined multiplication as 3 times 2, where adding the 0 in there handles the 2 other assumptions. Now, negative numbers are not counting numbers, is the next misinterpretation. If minus 3 times 2 is equal to minus 2 plus 2 plus 2, that would be equal to minus 6. And if minus 3 times minus 2 is equal to minus of minus 2 plus minus 2 plus minus 2, we get minus minus 6, which is 6. Now, it turns out that if we didn't define it with this minus sign in front of it, then we would get the wrong answers. So this gives us a little bit thought process is that we're actually defining how multiplication is done. And when we define it with a negative number so that we get the answers consistent with what we're doing, we find it becomes a counting number. Now, the commutative property can be derived from the distributive property. We basically say that 5 times 3 is equal to 5 times 1 plus 1 plus 1, which is 3, and we multiply it through, we get 3 5s added together, and that gives us 3 times 5. So that leaves us with 2 concepts out of the 5. That addition is commutative and that multiplication is distributive. Why is this important? Because multiplication, matrix multiplication, is not commutative. The current interpretation of the concept of zero and counting makes math more mysterious and more difficult and creates more inconsistencies. Now let's stray from the topic a little bit and let's look at factorials. I don't want to go into too much detail, but a factorial is number multiplied by its next lower number. Okay, and from that, we can discover what 0 factorial is. Okay, but we can't really find out what negative factorials and fractional factorials are until we go and use the integral calculus. That last form defines factorials for integers, irrational numbers, and complex numbers. Okay, so let's start with that little example where we're going from 1 over 0 factorial down to 1 over minus 4 factorial and showing how we're using that one formula to derive what those values are. Noticing that minus 2 factorial, 1 over minus 3 factorial is 2 divided by minus 1 factorial. Now, if we divide the 4 factorial by the 3 factorial, we get minus 3 factorial over minus 4 factorial. And using what we've found, we get minus 3. Now we seem to be dividing infinities or zeros. A lot of confusion in here. So how can we be more certain? Well, we could go to a calculator. Trouble with going to a calculator, it can't do that problem. So we go to differential calculus, where we go a little bit away from those numbers. We go a little bit above, we get some number close to minus 3, a little bit big, a little bit bigger or smaller. And for a little bit smaller than those numbers, we also get a close number to minus 3. And we could try a few numbers in between. And in mathematical discipline, we use that as the answer. Okay. And one more case we have showing how looking at math in this different way makes it possible to solve problems easier. We're using the commutative property to do our multiplication of 12 times 12, except we use number structure to break it up into 10 plus 2 times 10 plus 2. We go through using the distributive property, and notice along the way, we get 10 times 2 and 2 times 10. We're making use of the commutative property. When we go to 123 times 123, we make use of our previous work, and the 144 now becomes 144 with 2 zeros after it. And then we take that answer to help us with 1,234. Very little effort. And 12,345, again, little effort. Okay, and we do it the traditional way, we get the same answer. However, let's look at this simple little problem where we're multiplying 10 digits by 10 digits. It would be 10 lines of arithmetic. But, or 10 lines of multiplication. But here, it's 6 lines of no multiplication. We make use of the previous work. We use the numbers without zeros, taking advantage of what our understanding of number structure. We get a simple answer, which, by the way, I checked on the calculator to make sure it was correct. And we have a little example of number structure, which is showing that the 1, 2, 3, 4, 5 repeated twice is really 1, 2, 3, 4, 5 with 5 zeros after it, plus 1, 2, 3, 4, 5. And now in summary, 0 has the following properties. It's the integer before 1. It has a sign, and it simplifies number structure and multiplication. Negative numbers are counting numbers, except that we put a minus sign after we've done our counting. Multiplication is redefined as having a 0 added into it, so that we do not have to use the commutative property to prove that the multiplication by 0. And for multiplication, the commutative property is defined from the distributive property. So in conclusion, question whatever you're taught. Learn to understand and look for alternate proofs and ways to do a problem. You do not have to agree with what you are taught, but once you have learned to reason, you can have confidence in your way of doing things. Finally, convince somebody else that your interpretation is a more reliable way of looking at the problem. Your new love and skill in math will give you the confidence you seek. Here is some reference information so you can contact me if you choose to do so.